This is part 19 of 8086 instruction set, and we will see unconditional control transfer instructions. So control transfer instructions help us to alter the sequential flow of execution of a program. So altering sequential flow of execution means that either the contents of IP has to be changed or contents of CS and IP both has to be changed. Okay, so there can be two types of changes affected, right? One can be based on some condition, that is known as conditional branch instruction. It means that due to an effect of already executed instruction or due to a condition in the system, IP value or CS IP values are altered. Then we have unconditional branch instructions where CS IP combination or IP is altered just out of there, due to no particular reason. Okay, so we will first focus on unconditional branch instructions, and as I told earlier, IP or CS IP combination may be modified, okay, to affect the branch. So the first instruction is call, and call instruction is used to call a procedure in assembly language. Okay, so this is the format of call instruction. You will issue the call instruction followed by the label of the procedure. Then basically there are two types of calls. One is a near call and a far call. So a near call means you are calling a procedure which is residing in the same segment as that of the currently executing program. Okay, so when you are doing a call to a procedure that is in the same segment, what happens is only the IP needs to be changed, right? So what happens is the current IP, which is obviously the incremented IP or which points to the next instruction, is pushed into the stack, and then the IP is loaded, that is instruction pointer is loaded with the offset of the label, okay, where it is located within the current segment, so that we may start executing that particular line of code instead of the actual line of code which we were supposed to execute. Now suppose we are dealing with a far procedure, okay, a procedure which is lying in some other segment. What has to be done is CS as well as IP values both has to be changed. So what happens is the incremented IP, that is the current IP value as well as the current CS value, will be pushed into stack, and CS and IP will be loaded with new values so that execution may be passed on to the procedure that we are calling. Now once you call a procedure, right, you have to obviously return, then only you can resume your execution. So return from a procedure is done with an instruction named IRET, okay, return from procedure. So when this instruction is executed, what happens is we already have either IP or CS IP in stack, right? So they are restored back. Okay, so if we had already issued a call which is a near call, only IP will be there in stack, so that IP will be popped back into its older value. Suppose we had issued a for call, right, then we need IP as well as CS from the stack, and they are restored. So this is the case of call and return. Now apart from normal procedure invocation, we also have facilities to invoke interrupt service routines. Okay, so you obviously know what is an interrupt service routine. It is a procedure that has to be executed to service an interrupt, and we have both hardware as well as software sources of interrupt. So this int n instruction is used to invoke or trigger a software interrupt so that control can be passed to an interrupt service routine. Okay, so int n instruction is particularly special in the case that you can invoke any type of software interrupt provided if you change the value for n. Okay, so this n is a variable, so the format of invoking a software interrupt is int followed by the interrupt number which you would like to invoke. Okay, so you obviously know what happens when an interrupt is invoked. Suppose that we have an interrupt invocation line between these two addresses, that is 1020 and 1022. Okay, so when int n is executed, what happens is we need to get the location of the interrupt service routine, and you already know that interrupt service routines location is fed in interrupt vector table. Okay, so it is a separate table with segment 000h in 8086. Okay, so a table with base at 000h in 8086 with interrupt vector table, and note that it contains the locations to interrupt service routines for various sources of interrupts. Okay, so suppose we have an interrupt triggering over here. What happens is based on the interrupt number, a particular entry of this interrupt vector table will be taken. And what is the entry of an interrupt vector table? So the entry of an interrupt vector table is CS and IP values, which points to the interrupt service routine. Okay, so suppose that we have invoked int 20. Okay, so what happens is the interrupt number will be multiplied by 4, and that offset is found out within the segment starting at 000h. Okay, so that offset will actually give you the location of the ISR. Okay, so let's consider the case of int 20h. So 20h will be taken and multiplied by 4, so we have 80h. So 80h is the offset within the segment starting at 000h, okay, where you can find the interrupt vector. Okay, so this is the offset, right? So starting from this offset, for the next 4 bytes you can see the interrupt service routine's location. So it will be like the IP followed by CS. Okay, so the IP's lower byte will be starting at 80, offset 80, then you will have the higher byte of IP at 81, then the CS lower byte will be located at 82, and CS higher byte will be located at 83. Okay, so if you take all these things and load in IP and CS, then you are ready to run the ISR. Okay, so that is the use of int n. Int n will help you to go into a particular ISR corresponding to interrupt vector number. Okay, now we have certain interrupt instructions which are pretty straightforward, right? We have one such instruction, that is int o, that is interrupt on overflow. So how this works is int o, it will invoke ISR corresponding to 4, okay, interrupt number 4, if the overflow flag is set. Okay, so if there is already an overflow condition in the system, and if you invoke int o, that is interrupt on overflow, the ISR corresponding to the overflow condition, or the 4, right, interrupt vector number 4 will be invoked. So if you multiply 4 with 4, right, we will get 16. So 16 will be the offset within the interrupt vector table, and from that offset we will get the values to be populated to CS and IP, and hence the ISR corresponding to the overflow case will be executed. Okay, so we have found out the various ways to trigger software interrupts or enter into ISRs of software interrupts. Then how will we return from interrupt? Note that when we invoke an interrupt, right, many things are pushed into the stack, like the flag register, CS and IP, because obviously when you run an ISR, the system flag is going to get affected, and obviously CS and IP is going to change. Okay, so in order to get back to the previous position of the system or the state of the system, we need to preserve these things, right? So we have IRET, that is interrupt return instruction, which has to be present at the end of every ISR, so that all the things that we pushed into stack for preservation can be popped out. Okay, so IRET will be part of every ISR. Okay, at the end of every ISR, IRET will be there. It helps us to restore the system to the previous state by restoring the values of these registers. Okay, now we saw how to invoke a function or procedure. We saw how to invoke a interrupt. We also saw how to return from procedures as well as interrupts. Now we will see how to jump to any point of code. Okay, it is done using jump instruction, and in case of jump instruction you have to write the label or location to which where you are going to jump. Okay, so what happens when jump and a label name is specified is the CS and IP, right, either the combination of CS and IP or IP alone will be changed in order to facilitate this jump. So if you are going to jump within the same segment, only IP will be changed. If it is a inter segment jump, CS and IP will both be changed. Okay, now we will see the case of loop. Okay, looping is essentially alteration from the sequential execution, and looping or the loop instruction also takes the help of a label. That is, you need to mark a particular portion of the code to which or to where you are to jump repeatedly again and again. Okay, so this loop instruction, it actually takes CX as its counter for granted. Okay, so you have to load a particular value in CX register so that this loop instruction will iteratively jump to this label part till CX becomes 0. Okay, so when CX is not 0, the jump will happen. When cx becomes 0, the sequential execution will proceed. Okay, so this is how the loop instruction works, right? At the point of loop, what happens is this decrementing operation will happen, then this conditional check will happen, and if the condition is true, right, you will execute a jump to this label. So if you see this code, a particular line of this code is labeled, right? It is given a particular label or a name, and loop to that label is issued at the end. So this looping will happen only after this, right, the decrement of cx, and once cx is not 0, then you will proceed back to here. Then again sequential execution up to the loop portion will happen. Then again decrement operation of cx, checking whether cx is not 0. If it is not 0, jump will happen again. Suppose that cx is 0, what happens? We won't jump back to the label. We will proceed to remaining portions of the code which follows after the statement containing the loop, if any. Okay, so no jump, we will just continue the sequential flow. So that's how loop instruction works.